What? Do you think I forgot you? Welcome to the House of Cardioids. If we're gonna get into this, we should first talk about the circle. This is gonna come full circle in the end, but first, we need to talk about the circle. Now, traditional, this guy, boom. Okay, let's go. We're talking about R is sine theta. So our theta is changing. Our theta is the independent variable. Lots of variables in this house of cards. We go, and I pre-calculated these guys. The sine of 0 is 0, the sine of 15 is 2.6, the sine of 30 is 0.5, the sine of 45 is 0.71, the sine of 60 is 0.68. These are crude approximations. So if we're gonna go, and we're gonna graph these guys, boom, I got that guy, boom. 0 degrees, 0, boom, ha-ha. And then 15 degrees, boom, you go out that far. And then 30 degrees, you go out that far. And then 45 degrees, you go out that far. And then that far, and then that far. How far? We're rotating and we're going out. That far. Now at 90 degrees, now, I suppose we should be in radians, but you're more comfortable with degrees. So I'm keeping it in degrees. And now we're over here at 105. And now we're over here, boom. 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 0 again. Now what happens after 180 degrees? We see that our R is turning negative. Oh, don't be negative on this video. It's negative, so we're pointed in that direction, but we're going out that far. We're pointing in that direction, but we're going out that far. We're pointing in that direction, but we're going out that far. We're pointing in that direction and we're going out that far. That's what's going on all of these. What's going on? We're, boom, going out that far. And in the backwards direction, indicated by this bottle cap opener, yeah, Russo would get in trouble with that. You go out that far, and then you go out that far, and then you die in a car. What? Spoiler alert. Yeah, that was like season 1. But when we go and we connect all of these dots, it creates a circle. But it doesn't go around once. It goes around twice. What comes around, goes around. House of Cards. Do I look tired enough to be Kevin Spacey? Looks like I've had trouble counting by 15s. Whoops. A bullet grazed my cheek. But I haven't fallen. Indeed it is a treacherous path. We're on to the limaçon. Oh God, oh God! This guy, I'm graphing R plus 4 cosine theta when I start here in degrees. With our theta, our independent variable, we get out our R's. And boom! When theta is 0, we're at 0. Bam! Oh, no, just kidding. When theta is 0, it's 6. So you go out 6 far. Boom. Then at 15 degrees, we're at 5.9. Boom. Then at 30 degrees, we're at 5.5. Boom. So we're rotating and we're going out R far. So at 45 degrees, we're at 4.8, then 4, then 3, then 2, then 1. These are all approximations to the tense place. Boom! That was 90 degrees. At 105 degrees, we go out this far, and this is the interesting part. Our R is getting smaller and smaller and smaller and smaller and smaller and smaller and smaller until it's nothing. Boom. Then what happens? Our R goes negative. Yeah, our R is right here. When it goes negative right there, 135 degrees. So at 135 degrees, it goes boom, there. Then it goes 150 degrees. It's going negative. It's going negative. Bam. And then at 165 degrees, it's like there, boom. And now we're all half circle, and it's at deuces. And then now we're over here, and we're still going negative. Boom. Then boom. Then boom. Then our R is back to nothing. And then our R starts to go positive. Whoa. And then, whoa. We're over there now. And then, whoa. Please don't scratch the board. It's expensive. Then, whoa. Then, whoa. Get over there. Whoa. 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 And if we put that all together, it's all. Our first lemon. It's not the beginning of the story that I fear. It's not knowing how it ends. That's why every polar curve is fair game now. Forward is the battle cry. When the constant is much, much stronger than the function, you don't get a complete circle. You get a flattened circle. I'm talking about this guy down here. The constant is much, much bigger than the coefficient on the trigonometric function. When we're looking at these polar curves, when our angle is 0, boom, we go out 3 units. 15 degrees, that's 3.3 units. And then when we're at 30 degrees, that's 3.5 units. 45 degrees, 3.7. And then, 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 here's where the flattening happens. Down here, boom, 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 boom. Why? When the sign is negative, when it's below the line, the sign is negative and it's subtracting from 3, and all of these values are smaller than 3. When the sign is positive up here, it's adding to 3, and all of these values up here are bigger than 3. And that's why we see a flattening of the circle. It's a lemon. When a problem's on the ropes, that's when you throw a combination to the body and a hook to the head. Now things are getting real interesting. We're talking about the struggle between two factions, the struggle between what? The constant and the function. What happens when A and B are equal? When A and B are equal, we go through and we calculate a few values. Theta from 0 to 360. This will come full circle. When theta is equal to 0, boom. Yeah. We go out 3, because that's how we calculate that. When it's 15 degrees, we sees our function's 3.8. Then at 30 degrees, our function is 4.5. That means we rotate 60 degrees and we go out 5.6. Then we rotate 75 degrees and we go out 5.9. Then we rotate. This is forming the ribs of our cardioid. Boom. And we go around and we keep going out as far as they say, and then we have a cardioid. I feel like there's one missing right here. I don't know. But then when we go and we look at this guy and we have the ribs of our cardioid, it looks like it's gotta have a kink to be a cardioid. Dink. We continue to struggle with our cardioids. Maybe we should see a cardiologist. That last one was a little rough. This time, the constant is stronger than the function. When I say stronger, I mean the number is larger. When the number is larger but smaller than 2, we get something that looks like this. I've calculated some values, boom, for thetas and r's. We put our thetas in, we get our r's out. When theta is equal to 0, boom, we are out. 5 units, 15, boom, then this, then that and that, oh, then the yeah, okay, keep going, yeah, there you go, my heart. This problem, because we're going through and we're calculating those, feel free to put those in your calculators and see that these are gonna be the values for our cardioid. So if we want to see what the graph of 3 plus 2 cosine is gonna be, heart, a cardioid, and my heart pumps for another example. For those climbing to the top of the ladder, there can be no mercy.
I'd apologize about the audio being different, but I don't apologize about anything. We're talking about circles and lemniscates. Yeah, sure, it's a recap. The sine is y over r, so our r is going to go around the y-axis when we're dealing with sine. The sine bounces between -1 and 1, but you have negative r's in there too. That was in the review. This guy, boom, cosine, is x. That's why the circle's on x. And that's what I'm talking about next. No, wait. The maximum value of cosine is 1, so that's how big our circle is. If we had a coefficient in front of it, it would go out that far. Lemniscates. Here that coefficient is much bigger, so that means your r's are eventually going to be negative when the cosine's ever negative, so you get a loop-de-loop, and that last one was cosine, so it was on x, now sine. Okay, sure. So now we're getting a cardioid y, because they're eventually going to be equal y, because the sine is -1 when theta is 270. That's why we get that there. And then that 3 on the top, that should be a 6, because that's when the cosine is 90. That's 1. That means 3 plus 3 is 6. I'll catch that and edit. Explaining the 0. Okay. So what's next? Oh. More limaçons. This time, the coefficient is bigger. Alright, so what does that mean? That means when cosine's negative, it's never going to be 0. So what does that mean? That means you're never going to get 0, but it's going to subtract. When I say it, I mean the cosine. It's going to subtract from the 3, but it's going to subtract at most 2. So your smallest value is going to be 1. Your largest value is going to be 5, and that's what that is. The cosine of 0 is 1, so 2 plus 3 is 5. More lemniscate. That one's much, much bigger. That means when you're subtracting 1, doesn't mean much. And it's the sine, so it affects the y value. cosine affects the x value. When the sine of 0 is 0, so it starts at 3, boom, that big value right there, that should be 4. Why? Because the sine of 90 is 1, and 1 plus 3 is 4, so that's 4. It goes around, and then we get flat down here. Why? Because the sine is negative in the third and fourth quadrant, so it's subtracting from 3, and that's why it's flat down there, see? And I suppose this guy could have been a little bit more articulate about that. I don't know. Zoe, it's good to see you. I thought that I would never. Spoiler alert.
Hi, MathByFives!
Stuart, be careful! No!
Every kitten grows to be a cat. Hunt or be hunted.
So when we're here at 0, where do we start? At 0. And then, when we're at 15 degrees, you're out 0.5. So you rotate 15 degrees, and you go out half of 1 unit, and then you're at 30 degrees, and you're 0.68, and then you're 0.86, so a little bit further. And then where are we now, 45 degrees?
Yeah.
We're out at 1. At 1, this isn't looking right. And then at 75. How did that look at there?
You put an extra dot. You messed up already.
I did already?
Yeah.
Awesome.
Again.
Boom, boom. 0.8, 0.6, 1. Okay, and then 0.5 right there? Does it look right now?
Yeah.
So it's going this way?
Yeah.
Oh, and then we continue on. And then we continue on. Boom. And then here. Boom. And then here. Boom. And that's how the box and flower all started.
So how do we tell the difference between these roses? There. That's all the roses. And boom. That's when the argument is twice. Boom. Even roses. That's when the argument's 4 times. And that's when the argument is 6 times. We see we have a doubling when the argument is even.
A student is like a tree in a field. It leans whichever way the wind is blowing. After 15 years of teaching, I know which way the wind is blowing.
We're graphing these guys. This is a rose. I know because that's 3 theta. That means I'm gonna, when it's odd, I'm gonna have 3 petals. Let's go. When theta is 0, R is 1. When theta is 15, R is 0.07. I'm rotating this way and I'm going out that far. When theta is 30 degrees, I'm here at 0. Whoa. And then when theta is 45 degrees, I see that I'm facing this way, but my R is in the negative direction. So at 45 degrees, my R is out 0.7 in the negative direction. I'm going backwards. And then at 75, I'm out, a little further than that, sure. And then here, boom. Well, that's gonna be a short leaf. Anyway, and then I'm back here at 0. And now where? Now where? I'm up here, and then I'm up here, and then I'm over here, and then I'm back to 0, then I'm over here. So I start out here at 1, and then it's all whoop, de-whoop, de-whoop, and then I complete that loop when I get down to 1, and that's a 3-leaf polar rose.
The polar rose. Alright, when the argument has 3 times, it's this guy, because it has 3 petals. When the argument is 5 times, it's this guy, it's 5 petals. When the argument is 7 times, it's this guy, that guy. Alright, fine. So when the multiple is odd, you have that number of petals.
How quickly poor grades are forgotten when power and wealth are in the equation.
Oh boy! And then that happens. But in order for that to happen, we have to look at this guy. This dragonfly? No. This flower. Here we see our R's are positive, 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 R's are positive. And then we get to 45 degrees, and then our R switch to negative, 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 R's are positive, 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 positive. I'm trying to talk about what happens when we get rid of our negative R's. We get rid of our negative R's. All our negative R's become positive, so we still start in this direction. Whoa, it was going so negative. And then that's how you only get the 2 leaves on that. What was that one called? What'd you get when you Googled it?
Landscape.
Landscape.
I feel like there's cardioids everywhere. How do we tell them apart?
Y equals sine theta. That's a circle. Circle on the y-axis because sine represents y. When sine of pi over 2, that's 1. That's why that's out there and it goes around twice. R equals cosine theta. That's also a circle. But it's a circle on the x-axis because cosine represents x. So when cosine is 0, that's 1, and that's why it's there and it goes around twice. 1 minus cosine theta. That's a cardioid. Why? Because this matches that. So when cosine is 1, that's 0. When cosine is minus 1, that's 2. And that's why you see that shape there.
It's gotta have a kink to be a cardioid. Dink!
1.5 minus cosine theta is also a cardioid, but this time the constant isn't bigger than the coefficient, so it never actually reaches 0, but you do get that kink when the cosine is 0, and you do get that multiple when it's pi. 3 minus cosine, that's a lemicon. Why? Because when cosine of 0 is 1, that's 2. When cosine is pi, that's 4. And that's why you get the flattening of the circle on the x-axis. 1 minus 2 cosine theta. That's a lemicon. Why? Because the coefficient is bigger than the constant, and it's going to double on itself because it's going to have a negative r. Cosine 2 theta. That's a polar rose. Our argument's been doubled, so we're going to double the number of petals and we get 4, sure, because we're going to have negative r's. And it's cosine, so it starts on x. Cosine 3 theta is next. That's also a polar rose, but this time it's odd. The argument's odd, so we're going to get that number of petals, and it's cosine, so it starts on the x. R squared, cosine 2 theta. It's a lemniscate. Since r is squared, we lose all of our negative r's. They become undefined, and that's why we find our 4-leaf rose becomes a 2-leaf rose. It's a lemniscate.